Have you ever looked into the darkness between galaxies and wondered if empty space is really empty? Because to billion light years from Earth, astronomers found something that should not exist, not a black hole, not a galaxy, not a cluster of stars, a void, a region of space so enormous, so unnaturally empty that even after years of observation, scientists still struggle to explain how it formed. At first glance, a void might not sound impressive. Space is already mostly empty. Between stars, there is emptiness. Between galaxies, there is even more emptiness, but this is different. Imagine standing on a mountain and looking across an entire continent. Now imagine that continent contains no cities, no rivers, no forests, no roads, no signs of life whatsoever. Only endless emptiness stretching beyond the horizon. That would feel wrong. The universe felt the same way when astronomers discovered this structure because, according to everything we know about cosmic evolution, regions this large are not supposed to exist. The universe began almost 14 billion years ago after the Big Bang. Matter spread throughout space. Tiny fluctuations in density slowly grew under gravity. Over billions of years, those fluctuations became stars. The stars became galaxies. The galaxies gathered into clusters, and clusters connected together through gigantic cosmic filaments, creating what scientists call the cosmic web. If you could zoom far enough away from the universe, you would not see isolated galaxies scattered randomly through space. You would see something resembling a vast three-dimensional spider web stretching across billions of light years. Bright filaments packed with galaxies, dense clusters where thousands of galaxies gather together, and between them, dark empty regions called cosmic voids. Voids are normal. Expected. Necessary. They are part of the universe's architecture, but even normal voids have limits. Most measure tens of millions of light years across, some stretch to a few hundred million. Yet, this discovery shattered every expectation. The empty region astronomers found appeared to span nearly 2 billion light-years. To understand how absurd that is, consider this: the entire Milky Way galaxy is about 100,000 light years. Why? Light needs 100,000 years to cross it. This void is roughly 20,000 times larger. A beam of light entering one side would continue traveling for 2 billion years before reaching the opposite edge. When the first calculations appeared, many scientists assumed there had to be a mistake. The measurements were checked, then checked again. Different instruments examined the same region. Different research teams analyzed the data independently. Yet the anomaly remained. The universe appeared to contain an enormous hole, and the deeper astronomers looked, the stranger it became, because this void was not discovered by simply counting galaxies. Its existence first revealed itself through something far more mysterious: a cold spot, a faint scar hidden within the oldest light in the universe itself, a mark so unusual that some researchers began asking a question nobody expected to ask. What if this gigantic void wasn't merely empty space? What if it was evidence that something much stranger had happened billions of years ago? Something connected to the earliest moments after the Big Bang, something that may have left a permanent wound in the fabric of the cosmos. The discovery began with light, not ordinary light, not starlight, not sunlight, the oldest light in existence, a faint glow filling the entire universe known as the cosmic microwave background. This ancient radiation is the leftover heat from the Big Bang itself. Every direction you look in space, that light is there. It has been traveling across the cosmos for nearly 13.8 billion years. For decades, astronomers mapped it with increasing precision. At first, it appeared almost perfectly uniform, a smooth ocean of ancient radiation. But when scientists examined it closely, tiny irregularities emerged: minute temperature differences, fractions of a degree, small fluctuations that would later become galaxies, clusters, and cosmic structures. Most of these variations made sense. Theoretical models predicted them, computer simulations reproduced them. Everything seemed consistent until researchers noticed one particular region, a patch of sky significantly colder than it should have been. At first, it looked insignificant. A statistical anomaly, perhaps an error in the instruments, perhaps interference from our own galaxy. But the cold spot refused to disappear. Different satellites observed it. Different analyses confirmed it. The anomaly remained. The region appeared roughly 70 microkelvin colder than surrounding areas. That may sound tiny, and it is. But in cosmology, tiny differences can reveal enormous truths. The problem wasn't merely that the spot existed. The problem was its size. It covered a huge portion of the sky. Far larger than expected from random fluctuations alone. The odds seemed uncomfortable, not impossible, but uncomfortable. Scientists began debating what could create such a feature. One explanation soon emerged. Perhaps something gigantic existed between Earth and that ancient radiation, something capable of altering the light as it traveled toward us. That idea led astronomers to search the region more carefully than ever before. Large galaxy surveys began mapping the area. Millions of galaxies were cataloged, distances measured, three-dimensional maps constructed, and slowly a strange pattern appeared. There were fewer galaxies there. Far fewer. At first, the deficit seemed modest. Then the data accumulated. The emptiness became impossible to ignore. Entire stretches of space appeared almost deserted. Clusters vanished. Filaments weakened. The normal cosmic web seemed torn apart. Instead of dense structures, astronomers found vast regions with remarkably little matter. It was as if someone had scooped enormous chunks out of the universe. The more researchers measured, the larger the structure appeared, hundreds of millions of light years. Then over a billion. Eventually approaching scales so enormous that even veteran cosmologists struggled to describe them because, according to standard cosmological theory, structures grow gradually through gravity. Matter pulls matter. Small regions become larger. Galaxies gather together. Clusters form, yet there is a limit. The universe has not existed long enough for gravity alone to create structures of arbitrary size. At some point the numbers stop making sense, and this void was approaching that point. Some researchers proposed that the cold spot and the giant void were directly connected. As ancient microwave radiation traveled through the empty region, it lost energy. By the time the light reached Earth, it appeared slightly colder. The explanation sounded elegant. Simple. Almost perfect. For a brief moment it seemed the mystery had been solved, but then another problem appeared. The void wasn't large enough, not even close. Calculations revealed that even an enormous cosmic void could only explain part of the temperature anomaly. The cold spot remained too cold. The numbers still didn't match. Something was missing. The universe was giving to clues. A gigantic empty region and an ancient cold scar and primordial light, yet neither clue fully explained the other. Instead, each discovery deepened the mystery. And as researchers searched for answers, some began considering possibilities that sounded almost impossible, possibilities involving quantum fluctuations, parallel universes, and collisions between entire realities long before galaxies even existed. If the giant void could not fully explain the cold spot, then something even more unsettling had to be considered, and that is when the conversation drifted from astronomy into territory that sounded dangerously close to science fiction. For decades, cosmologists believed they had a reasonably solid understanding of how the universe evolved after the Big Bang. Not a complete understanding. There were still mysteries, dark matter. Dark energy. The origin of inflation. But the broad picture seemed stable. The universe began extremely hot and dense. Space expanded. Tiny quantum fluctuations became the seeds of every future galaxy. Gravity amplified those fluctuations. Stars formed. Galaxies assembled. Clusters emerged. The cosmic web took shape. Everything followed a predictable chain of events. The cold spot threatened that confidence. Because if neither ordinary fluctuations nor the giant void could fully account for what astronomers were seeing. Then perhaps the source of the anomaly was much older, much deeper. Perhaps it originated before galaxies, before stars, before the cosmic web itself. Perhaps its roots stretched back to the first fraction of a second after the Big Bang. To understand why this possibility terrified cosmologists, we need to talk about inflation. Inflation is one of the strangest ideas in modern science. According to the theory, the universe did not simply expand after the Big Bang for an unimaginably brief instant. It exploded outward faster than the speed of light, not because matter moved faster than light, but because space itself expanded. A tiny region smaller than an atom suddenly ballooned into something vastly larger. This incredible expansion happened in less than a trillionth of a second, yet it shaped everything that came afterward. Without inflation, galaxies might never have formed, stars might never have existed. You would not be here. Neither would Earth. Or the Milky Way, or anything else. Inflation solved several major cosmological problems so successfully that many scientists now consider it an essential part of the universe's history. But inflation introduced a new mystery, a very disturbing one, because some versions of inflation never completely stop. In these models, inflation ends in one region of space but continues elsewhere. One bubble universe forms, then another. An endless cosmic foam of universes emerging from a larger inflating background, each bubble potentially containing different physical conditions, different histories, possibly even different laws of physics. This idea became known as eternal inflation, and if eternal inflation is correct, then our universe may not be the only universe. It may simply be one bubble among countless others. For years this remained purely theoretical. Interesting. Mathematically possible, but impossible to test. Then some physicists noticed something. If two expanding bubble universes formed close together in the early cosmos, they might eventually collide, not violently, in the way planets collide, not with explosions, but with distortions. Ripples. Scars imprinted into the structure of space itself. The collision would leave a mark, a permanent fingerprint visible billions of years later, and suddenly the cold spot looked very interesting because one prediction of certain bubble collision models is the appearance of large circular anomalies in the cosmic microwave background. Regions slightly hotter or colder than expected. Regions that stand out from normal fluctuations. Regions suspiciously similar to what astronomers were observing. The idea spread rapidly through the cosmology community. Could the cold spot be evidence that our universe brushed against another universe long ago? Could that strange scar in ancient light be the aftermath of a collision between realities? It sounded absurd. Yet the mathematics did not immediately rule it out. Researchers began constructing simulations. Thousands of virtual universes, millions of artificial microwave sky maps. They compared those simulations to real observations. Most results favored ordinary explanations. Random fluctuations remained possible. The giant void remained possible, but the bubble collision scenario refused to disappear entirely. It lingered, a possibility sitting at the edge of serious science, neither confirmed nor eliminated, and that uncertainty created a fascinating problem. Because if the cold spot truly represented evidence of another universe, then it would become one of the most important discoveries in human history. Not merely an astronomical discovery, not merely a cosmological discovery, a discovery that would fundamentally redefine reality itself. For the first time, humanity would possess observational evidence that our universe is not alone, that what we call the universe might actually be part of something much larger. Something we have only begun to imagine. Yet even that possibility was overshadowed by another question. A question even more difficult to Answer: because regardless of how the cold spot formed, one fact remained unchanged. The giant void itself was real, billions of light years of extraordinary emptiness, a region so vast that astronomers still struggle to understand how gravity, matter, and cosmic evolution could have produced it, and the deeper researchers mapped that emptiness, the more they began to suspect that the void might not simply be a missing piece of the universe. It might be telling us that our entire understanding of large-scale cosmic structure is incomplete. The deeper astronomers looked into the giant void, the more uncomfortable the situation became, because the problem was no longer the cold spot. The problem was the void itself, even if the cold spot eventually receives a perfectly ordinary explanation. The existence of such an enormous empty region still demands an answer, and so far no answer has been completely satisfying. To understand why, imagine the universe as a growing city. Over billions of years, neighborhoods develop. Roads connect them. Districts expand. Population clusters emerge. Some areas become crowded, others remain sparsely populated. That is normal. But now imagine discovering a completely empty region larger than entire countries combined. No cities. No towns. No roads. Nothing. A gigantic hole where development seemingly never happened. That would immediately raise questions. What prevented growth there? Why is it so different from everything around it? Was something removed? Or was something never there in the first place? Cosmologists found themselves asking the exact same questions because, according to modern simulations, the universe should not produce many structures this extreme. Computer models recreate cosmic evolution with remarkable accuracy. Researchers input the laws of physics. Dark matter distributions, initial conditions after the Big Bang. Then they allow gravity to operate over billions of years. The result is astonishing. Galaxies emerge naturally. Clusters form naturally. Voids appear naturally. The simulations successfully reproduce much of the observable universe, yet structures approaching the size of this giant void remain exceptionally rare, not impossible, but rare enough to make scientists nervous. And in science, nervousness is often where discoveries begin. Every major revolution starts the same way. The data refuses to behave. At first, researchers assume the observations are wrong, then they assume the calculations are wrong. Then they assume the instruments are wrong. Only after exhausting every other possibility do they begin considering that their understanding might be incomplete. The giant void pushed many cosmologists toward that uncomfortable stage because every year the measurements improved. Galaxy surveys became larger, distances became more accurate. Computers became more powerful, yet the basic mystery remained. The emptiness was still there, and it was enormous. One reason the void causes so much trouble is scale. Human beings are terrible at imagining cosmic distances. Even astronomers struggle. Numbers become meaningless beyond a certain point. Millions. Billions. Trillions. The words stop creating mental images. So let's put the size into perspective. The Andromeda Galaxy is approximately 2.5 million light-years away. A giant distance by ordinary standards. Light leaving Andromeda today will not reach Earth for 2.5 million years, yet a 2 billion light-year void could fit the Earth-Andromeda distance roughly 800 times across. Think about that. 800 Andromeda separations. Nothing. No major structures. No dense concentrations of galaxies. Just vast stretches of comparative emptiness. And that emptiness creates another strange effect. Gravity itself behaves differently there. Most people think of gravity as a force that pulls objects together. That is true, but on cosmic scales, gravity also creates motion by pulling objects away from underdense regions. Imagine standing between two mountains. Each mountain pulls you toward itself. If one mountain suddenly disappeared, the remaining mountain would dominate. You would begin moving toward it. The giant void works similarly. Galaxies surrounding it feel stronger gravitational attraction from dense regions beyond the void than from the empty region itself. As a result, galaxies appear to flow away from the void. The emptiness effectively expands, not because space inside it is growing faster, but because matter continues abandoning the region. Over billions of years, this process exaggerates differences. Dense regions become denser. Empty regions become emptier. Yet even this mechanism struggles to explain the largest observed voids. Gravity can enlarge emptiness, but can it enlarge emptiness this much? That question remains controversial. Some researchers argue yes, others remain unconvinced, and then there is dark matter, the invisible substance believed to make up most of the universe's matter content. Dark matter does not emit light, does not absorb light, does not reflect light. Yet its gravity shapes galaxies and cosmic structures everywhere. In many ways, dark matter is the skeleton of the universe. Visible matter merely follows its framework, which leads to an intriguing possibility. Perhaps the giant void is not merely empty of galaxies. Perhaps it is unusually empty of dark matter as well. If true, that changes everything, because galaxies can disappear while dark matter remains. Stars can be absent while gravitational structure survives, but removing both visible matter and dark matter requires something much more dramatic. Something affecting the universe at a fundamental level. Researchers begin exploring increasingly exotic possibilities. Perhaps the initial quantum fluctuations after inflation were unusually weak in that region. Perhaps dark matter behaved differently there. Perhaps some unknown process suppressed structure formation billions of years ago. Perhaps the void is a relic from conditions that no longer exist anywhere else in the cosmos. Every explanation solved part of the puzzle, none solved all of it, and the mystery became even stranger when astronomers started comparing the giant void to the largest known structures in existence. Because the universe contains objects so vast they already challenge conventional expectations. Gigantic walls of galaxies stretching across hundreds of millions of light years. Massive superclusters connected through immense filaments, structures so enormous that they seem to violate the assumption that matter should become statistically uniform on very large scales. The giant void appeared to belong to this same category, a growing list of cosmic features that seem larger than theory comfortably allows. One anomaly might be ignored. Two anomalies might be coincidence, but when multiple structures begin appearing near theoretical limits, scientists start paying attention. Because sometimes nature is trying to reveal something, not through dramatic discoveries, not through obvious contradictions, but through subtle patterns hidden inside the data. Patterns suggesting that the universe may be more complicated than our current models assume. And if that possibility is true, then the giant void is not merely an empty region of space. It is a warning, a clue. A message buried within billions of light years of darkness. A message suggesting that somewhere in our understanding of cosmic evolution, something important may still be missing. And the most unsettling possibility of all is that the void may not be unique, because recent surveys have begun uncovering additional regions of unusual emptiness throughout the observable universe, smaller than the giant void, but disturbingly similar. As if the cosmos contains scars repeated across unimaginable distances, scars that may all trace back to the same unknown cause, a cause that existed long before the first galaxy ever formed. The giant void would already be one of the strangest structures ever discovered if it existed alone, but it doesn't, and that is where the story becomes far more unsettling. Because once astronomers began mapping the universe on truly enormous scales, they discovered something unexpected. The cosmos was not merely producing giant empty regions, it was also producing gigantic structures. Structures so large that many researchers were forced to ask whether the universe itself was following the rules we thought it followed. For most of the 20th century, cosmology relied on a principle so fundamental that it was rarely questioned. The cosmological principle, its basic idea is simple. On sufficiently large scales, the universe should look roughly the same everywhere, not identical, not perfectly uniform, but statistically similar. If you zoom out far enough, local irregularities should disappear. Galaxies should blur together into a smooth cosmic distribution, large structures should eventually average out, the universe should become homogeneous. That assumption forms the foundation of modern cosmology. Without it, many of our equations become dramatically more complicated. Many of our models become less reliable. Many of our predictions become uncertain. And for decades, observations appeared to support it. Then astronomers started discovering monsters, not literal monsters. Cosmic monsters. Structures so enormous that they seemed to push against the limits of what should exist. The first discoveries were surprising. Then they became troubling. The Sloan Great Wall, over 1 billion light-years long, a colossal arrangement of galaxies stretching across space like a continental fracture. Then came even larger candidates, the huge LQG, a giant quasar group extending approximately 4 billion light-years. Then the Hercules Corona Borealis Great Wall, a structure so enormous that estimates placed it at nearly 10 billion light-years across, nearly a tenth of the observable universe. When astronomers announced these discoveries, reactions were mixed. Some researchers were excited, others were skeptical. Many questioned whether the structures were truly connected or merely statistical coincidences. The debates continue today. Yet one fact remained difficult to ignore. Nature kept producing things near theoretical limits. Again and again. And again, gigantic walls, gigantic clusters, gigantic filaments. And now gigantic voids. Individually, each discovery might be explained. Collectively, they formed a pattern that some cosmologists found increasingly uncomfortable because every time a structure grows larger, the assumption of large-scale uniformity becomes harder to test. The giant void sits directly in the middle of this debate. It is the opposite of a great wall. A great wall represents too much structure, too much clustering. Too much matter. The giant void represents too little clustering. Too little matter. Too much emptiness. Yet both challenge the same underlying expectation. Both force scientists to ask whether the universe's largest scales are behaving exactly as predicted. Imagine flipping a coin 100 times. You expect roughly 50 heads and 50 tails. Not exactly. But close. Now imagine repeating the experiment thousands of times and continually finding bizarre results. 80 heads, 90 tails, long improbable streaks. Eventually you begin wondering whether the coin is truly behaving randomly. Cosmologists sometimes feel the same way about the universe. The standard model works extraordinarily well. It explains the cosmic microwave background, galaxy formation. Dark matter behavior, large-scale expansion, countless observations, yet every so often the universe reveals something that seems slightly too extreme, a structure slightly too large, a void slightly too empty, a pattern slightly too unlikely. Not enough to break the model, but enough to raise eyebrows, and that brings us to one of the most fascinating possibilities. What if these giant structures are not anomalies at all? What if they are clues? What if they are telling us that the earliest moments of cosmic history were more complicated than we realize because every galaxy, every cluster. Every filament. Every void ultimately traces its origin back to tiny quantum fluctuations during inflation. Those microscopic fluctuations became the seeds of everything. The entire cosmic web emerged from them, the stars, the galaxies, the planets. Everything. Now imagine that inflation itself was not perfectly smooth. Imagine certain regions experienced slightly different conditions. Tiny variations, almost imperceptible differences. For billions of years those differences would grow. A slightly denser region could become a giant wall. A slightly emptier region could become a giant void. Small causes, enormous consequences. Some theoretical models suggest exactly this possibility. They propose that inflation may have generated rare superfluctuations, extremely unusual patches that expanded into gigantic structures billions of years later. If true, the giant void might not be abnormal. It might be an ancient fossil, a surviving imprint from the birth of the universe itself, a relic dating back almost 14 billion years. That idea is simultaneously exciting and terrifying because if these structures preserve information from inflation, then they become windows into an era we cannot otherwise observe, the first fraction of a second after the Big Bang. An epoch so extreme that no laboratory on Earth can recreate it. An epoch hidden behind a wall of physics we barely understand. Suddenly, the giant void stops being an empty hole. It becomes evidence from a time before galaxies existed, before stars ignited. Before atoms formed, before the universe became recognizable. And yet there is another possibility, one that some physicists find even more intriguing. Because the giant void may not simply reveal how the universe formed. It may reveal how the universe evolves today. Specifically, it may be connected to the most mysterious substance ever discovered. A force so powerful that it dominates the entire cosmos. A force pushing galaxies apart. A force accelerating the expansion of reality itself. A force we call dark energy. Because if dark energy behaves differently inside giant voids than it does elsewhere, then these vast empty regions may be among the most important laboratories in existence. Not laboratories built by humans, but laboratories built by the universe itself, and hidden within their immense darkness may be clues about the ultimate fate of everything. The fate of galaxies. The fate of stars, the fate of space itself, and perhaps even the fate of the universe. If giant voids are fossils from the birth of the universe, they are remarkable, but if they can reveal the nature of dark energy, they may be even more important than anyone imagined, because dark energy is not simply another cosmic mystery. It is the mystery, the single largest unknown component of the universe, everything you have ever seen. Every planet, every star, every black hole. Every galaxy. Every cloud of gas. Every atom in your body. Together they account for less than 5% of the cosmos. 5%, that means 95% of reality consists of things we do not fully understand. About 27% appears to be dark matter, and nearly 68% appears to be something even stranger. Dark energy. An invisible phenomenon responsible for one of the most shocking discoveries in scientific history. The discovery that the universe is not merely expanding. It is accelerating. That revelation arrived in the late 1990s. Astronomers were studying distant exploding stars known as Type Ia supernovae. These stellar explosions are useful because they act as cosmic measuring tools. Their brightness is predictable. By comparing how bright they should appear with how bright they actually appear, researchers can calculate distance. The goal seemed straightforward. Measure how quickly cosmic expansion is slowing down, because everyone expected gravity to be acting like a brake. Galaxies pull on galaxies. Matter attracts matter. The expansion left over from the Big Bang should gradually weaken. At least that was the expectation. The observations said otherwise. The distant supernovae appeared dimmer than predicted, farther away than expected. The only explanation that fit the data was astonishing. The universe was not slowing down. It was speeding up. Something was pushing galaxies apart. Something was overcoming gravity itself. Something was accelerating the expansion of space. That something became known as dark energy. More than 2 decades later, we still do not know what it is. Think about that for a moment. The dominant component of the entire universe remains unidentified. We can measure its effects. We can estimate its abundance. We can observe its influence on cosmic expansion. Yet we still do not know what it actually is. Some physicists believe dark energy is a property of empty space itself. Vacuum energy, a subtle energy embedded within the fabric of reality. Others suspect something more exotic, a dynamic field evolving over time. An unknown force, evidence of new physics beyond Einstein. Nobody knows for sure, and this uncertainty is where giant voids become fascinating, because voids are among the emptiest regions in existence. They contain fewer galaxies. Less matter, less gravity, Less interference. If dark energy truly dominates the universe, its effects should become especially visible inside these enormous empty regions. Imagine trying to hear a whisper inside a crowded stadium. Impossible. The noise overwhelms everything. Now imagine listening in a silent desert. The whisper becomes easier to detect. Cosmic voids function similarly. The gravitational noise is reduced. The influence of dark energy may become easier to observe. For this reason, some researchers call giant voids natural laboratories. Not because they contain something, but because they contain almost nothing, and sometimes emptiness reveals more than matter. Astronomers began studying how galaxies move near large voids. The results were intriguing. Galaxies surrounding voids appear to flow outward, away from the emptiness. The larger the void, the stronger this effect can become. Part of this behavior is expected. Gravity naturally pulls matter toward denser regions, but some scientists wondered whether dark energy might amplify the process. Could voids act as magnifying glasses for cosmic acceleration? Could they reveal subtle behaviors invisible elsewhere? The question remains open, yet increasingly sophisticated surveys continue searching for answers. Massive projects now map millions of galaxies across enormous volumes of space. Every year, our three-dimensional map of the universe becomes more detailed. Every year, giant voids become easier to identify. Every year, new measurements refine our understanding of how matter moves through the cosmic web, and occasionally those measurements reveal something unexpected. One particularly intriguing idea suggests that dark energy may not be perfectly uniform. Perhaps its strength varies slightly across the universe. Perhaps some regions experience stronger acceleration than others. If true, giant voids could be locations where these variations become visible. The consequences would be enormous. Modern cosmology assumes that dark energy behaves consistently throughout space. Many calculations depend on that assumption. If the assumption fails, parts of our cosmological framework may require revision. Not abandonment, but revision. And history shows that revisions often lead to revolutions. Einstein revised Newton. Quantum mechanics revised classical physics. Every generation believes its understanding is nearly complete. Then nature reveals another layer. Another surprise. Another mystery hiding just beyond the horizon. The giant void may represent one of those moments. A place where observation is pushing theory toward its limits. A place where the universe appears to be whispering something we do not yet understand. And there is another reason scientists are so interested in these vast regions of emptiness, because some theories predict that voids should evolve differently depending on which model of gravity is correct. Most cosmology relies on Einstein's general relativity. The theory has passed every major test for more than a century. Black holes, gravitational lensing, time dilation, gravitational waves. Again and again, Einstein's equations prove astonishingly accurate, yet general relativity may not be the final word. Many physicists suspect a deeper theory exists, a theory capable of unifying gravity with quantum mechanics, a theory capable of explaining dark matter and dark energy, a theory capable of describing reality at every scale. If such a theory exists, giant voids may help reveal it. Because modified gravity models often produce slightly different predictions for how voids grow. Different expansion rates, different galaxy motions, different distributions of matter. The differences are subtle but measurable. Some scientists, therefore, view giant voids as testing grounds for the future of physics itself. Not merely cosmology. Physics. The fundamental laws governing reality, and if those laws behave differently than we currently believe, the first clues may emerge from places that appear completely empty, which is a strange thought, one of the greatest. Discoveries in scientific history may not come from studying what exists. It may come from studying what doesn't, from examining billions of light years of darkness. From measuring the shape of absence itself. And as researchers continued investigating these immense cosmic deserts, another disturbing realization began to emerge. The giant void might not simply influence galaxies. It might influence the light crossing through it, the oldest light in the universe, the cosmic microwave background. The same ancient radiation connected to the mysterious cold spot, and that realization would reopen the question many scientists thought they had already answered. What if the giant void is not merely a structure? What if it is part of a much larger phenomenon still hiding in the deepest layers of the cosmos? By this point, astronomers had identified two mysteries. The first was the giant void itself. The second was the cold spot embedded within the oldest light in the universe. For years, many researchers hoped the two mysteries would explain each other. Find the cause of one, and the other might disappear. Simple, elegant, satisfying. But the universe rarely chooses the simplest path. The deeper scientists investigated, the more complicated the relationship became, because the question was no longer whether the giant void existed. The question was whether it was powerful enough to affect light traveling across billions of light years of space. At first glance, that sounds impossible. A void is empty. How can emptiness affect anything? The answer lies in gravity. Even the absence of matter can shape the universe. To understand why, imagine a cyclist moving across a landscape filled with hills and valleys. Whenever the cyclist descends into a valley, they gain speed. When they climb out, they lose speed. If every valley and hill remains unchanged, the gains and losses balance perfectly. The cyclists finish with the same energy they started with. For a long time, scientists assumed light behaved similarly when crossing the universe. Photons travel through gravitational fields constantly. They fall into regions of stronger gravity. They climb back out, the effects cancel, nothing changes. Then researchers realized something important. The universe is expanding. And because the universe is expanding, the gravitational landscape itself evolves. While the photon is traveling, the hills move. The valleys change, the cosmic terrain is not static. And that changes everything. This phenomenon became known as the integrated Sachs-Wolf effect. The name sounds technical. The idea is surprisingly intuitive. Imagine entering a valley that slowly becomes shallower while you are inside it. You gain energy falling in, but when you climb out, the valley is no longer as deep. You lose less energy than you gained. The result is a small net change. Light experiences something similar when traveling through evolving gravitational structures. And giant voids are among the most important structures capable of producing this effect. When ancient microwave photons from the Big Bang pass through a massive void, something unusual happens. The photons enter an underdense region. They interact with a gravitational environment that is changing as cosmic expansion continues. By the time they emerge, they may carry slightly less energy than expected. To observers on Earth, they appear colder. Immediately, cosmologists became excited. This was exactly the kind of mechanism needed to explain the cold spot. A gigantic void could reduce the energy of microwave background photons. The cold spot could therefore be the shadow of a cosmic void. A simple explanation, a beautiful explanation. An explanation rooted in known physics. For a while, it looked like the mystery might finally be solved. Then the calculations arrived, and the calculations created another problem. The effect wasn't strong enough. Not even close. Researchers built increasingly detailed models. They estimated the void's size, its density, its geometry, its location. Its evolution. Everything. The result remained frustratingly consistent. The void could explain part of the cold spot, but only part, depending on the model, perhaps 20%, perhaps 30%, perhaps 40%, not 100%. There was still missing cooling, still missing temperature difference, still missing mystery. The cold spot remained colder than theory predicted. This realization split the scientific community. Some researchers argued that the discrepancy wasn't important. Perhaps the void was slightly larger than estimated. Perhaps observational uncertainties remained. Perhaps multiple smaller structures contributed. Eventually, the numbers might align. Others disagreed. They argued the mismatch was significant. If the void could not fully explain the cold spot, then another mechanism must be involved, and if another mechanism was involved, then the story was not finished. The debate continues today. Neither side has completely won. Neither side has completely lost. The cold spot exists. The giant void exists. The connection exists. The question is whether the connection explains everything or only part of the story. This uncertainty became even more intriguing as observational technology improved. New galaxy surveys pushed deeper into space. New microwave background maps reached unprecedented precision. Computers generated increasingly realistic simulations of cosmic evolution. Scientists expected clarity. Instead, they found complexity because the cold spot itself began displaying subtle characteristics that made interpretation difficult. Its shape appeared unusual. Its profile seemed slightly different from what some simple void models predicted. Nothing dramatic. Nothing impossible. Just enough to keep the argument alive. And when an argument survives for decades in science, it usually means reality is refusing to give up its secrets easily. One particularly fascinating possibility emerged from this uncertainty. What if the cold spot is not one phenomenon? What if multiple effects overlap? Imagine hearing a strange sound in the darkness. You assume it comes from one source. Later, you discover several different sounds occurring simultaneously. Individually, they seem ordinary. Together, they create something unexpected. Some cosmologists suspect the cold spot may be similar. Part giant void. Part statistical fluctuation. Part cosmic evolution. Perhaps no single explanation accounts for everything. Perhaps multiple processes combine to create the anomaly we observe today. The universe often behaves this way. Reality rarely organizes itself around human preferences for simple answers, and yet there remained a more radical possibility. A possibility that refused to disappear entirely because, despite decades of analysis, no conventional explanation completely eliminated the anomaly. The cold spot continued to sit there, silent, persistent, watching, like a scar left by an event nobody fully understood. And whenever conventional explanations struggle, more speculative ideas inevitably return. Ideas involving inflation, quantum fluctuations, bubble universes. Ancient cosmic collisions, concepts that sound almost absurd until you realize something unsettling. The data has never completely ruled them out. Most cosmologists do not believe the cold spot proves the existence of another universe. The evidence is nowhere near that strong, but neither can they entirely dismiss the possibility, and that tiny uncertainty is enough to keep the idea alive. Because if the cold spot truly represents evidence of something beyond our universe, then the giant void may not merely be a structure inside reality. It may be a signpost pointing beyond it, a possibility so extraordinary that many scientists prefer not to think about it, yet the mathematics continues to allow it, and the observations continue to leave the door slightly open, only slightly, but open nonetheless. The deeper humanity looks into the giant void, the more it begins to resemble a crossroads. One path leads toward conventional cosmology, refined measurements, better surveys, improved models. The other path leads somewhere far stranger, toward questions about inflation, the multiverse, and whether our universe is truly the entire story. Because if the giant void and the cold spot are connected to events that occurred during the earliest moments of cosmic history, then they may preserve information from an era we cannot directly observe. An era before galaxies, before stars. Before atoms, before light itself was free to travel. An era when reality may have looked nothing like the universe we know today, and hidden within that unimaginably ancient epoch may be the true origin of the giant void. A story that begins not billions of light years away in space, but billions of years ago, at the very dawn of existence itself. To understand the possible origin of the giant void, we must travel farther back than any telescope can see. Farther back than galaxies, farther back than stars, farther back than atoms, farther back than light itself, we must travel to a time when the universe was less than a fraction of a second old. A time so extreme that every law of physics we know begins to blur. A time when reality itself may have been fundamentally different. Most people imagine the Big Bang as an explosion, a single moment when everything suddenly burst outward into empty space. That picture is useful, but it is not entirely accurate. The Big Bang was not an explosion inside space. It was the expansion of space itself. Every region of the universe expanding simultaneously. Every point moving away from every other point. No center. No edge, just expansion. For an incredibly brief moment after the Big Bang, the universe existed in a state almost impossible to imagine. Temperatures exceeded anything nature has produced since. Matter as we know it did not exist. Atoms did not exist. Light could not travel freely. The entire observable universe was compressed into a volume smaller than a grain of sand. And then something extraordinary happened. Inflation. One of the most dramatic events in cosmic history. During inflation, space expanded at an absurd rate. Not fast. Not incredibly fast. Absurdly fast. In less than a trillionth of a second, the universe expanded by an unimaginable factor. A region smaller than a proton suddenly became vastly larger than entire galaxies. The scale of this expansion defies intuition. If an ordinary object expanded the same way, a microscopic speck would instantly become larger than the observable universe. This event shaped everything: the galaxies, the stars, the planets, the cosmic web, the giant void, even you. Everything traces its origins back to inflation. And yet inflation introduced a profound mystery. Because inflation was not perfectly smooth, quantum mechanics guaranteed that it couldn't be. Even in the earliest moments of existence, tiny quantum fluctuations existed, microscopic differences. Incomprehensibly small irregularities. At the time they were insignificant. Subatomic. Almost meaningless. But inflation magnified them. Tiny fluctuations became enormous structures. A microscopic excess of energy became a future galaxy cluster. A microscopic deficit became a future void. The entire large-scale structure of the universe emerged from these amplified quantum imperfections. That realization remains one of the strangest discoveries in science. Every mountain, every ocean, every city, every living creature ultimately traces its origins back to quantum fluctuations occurring during the first moments of cosmic history. Reality itself grew from microscopic uncertainty, and this brings us directly back to the giant void, because some cosmologists believe the void may represent one of the largest surviving inflationary imprints in existence, a fossil from the dawn of reality. Imagine a tiny region during inflation, slightly less dense than its surroundings, not dramatically different, just slightly, a minute quantum fluctuation. Normally, such a fluctuation would grow into an ordinary void. Large. Interesting. But not extraordinary. The giant void requires something more. Something bigger, something rarer. A fluctuation so unusual that it stood out even among the chaotic conditions of the early universe. The odds of such a fluctuation occurring are extremely low, but not zero. And given the immense size of the observable universe, even incredibly unlikely events can happen somewhere. This idea fascinates many cosmologists because it does not require new physics. No parallel universes. No exotic particles. No unknown forces. Just inflation operating exactly as expected, the giant void becomes an extraordinarily rare statistical event. Unlikely. But possible. Yet other researchers remain unconvinced, because the larger the void becomes, the more improbable the required fluctuation appears. Eventually, the numbers become uncomfortable, not impossible, just uncomfortable, and that discomfort has encouraged more radical theories. Some of those theories focus on the inflation field itself, the mysterious mechanism responsible for driving inflation. Nobody knows exactly what the inflation field was. We know what it accomplished. We do not know what produced it. Certain models suggest inflation may have behaved differently in different regions. Tiny variations in the field could generate enormous differences billions of years later. A region experiencing slightly altered inflation could emerge as a gigantic underdensity, a cosmic scar preserved across nearly 14 billion years of history. Other theories go even further. They suggest inflation may have occasionally produced defects in spacetime itself. Not holes, not tears, but subtle irregularities, ancient relics left behind as the universe expanded. These relics could influence matter distribution on enormous scales, potentially creating structures far larger than standard models predict. Again, none of these ideas have been proven, but they illustrate how seriously scientists take the problem. The giant void is not merely another astronomical curiosity. It touches some of the deepest questions in existence. Questions about why the universe looks the way it does. Questions about how structure formed. Questions about whether inflation occurred exactly as we believe, and perhaps most importantly, questions about whether our current cosmological model is complete. Because every time researchers trace the giant void backward through cosmic history, they eventually arrive at the same destination. The first moments after the Big Bang, the point where our understanding becomes uncertain, the point where observation ends and theory begins, a boundary beyond which physics remains incomplete. And it is precisely at that boundary where some of the most extraordinary possibilities emerge. Possibilities involving not merely inflation, not merely giant fluctuations, but entire regions of reality separating from one another during the birth of the cosmos. Regions that may have evolved into completely different universes, regions whose existence could explain why some anomalies seem almost impossible within our own. And if even a small fraction of those ideas are correct, then the giant void may not simply be a relic of cosmic history. It may be one of the closest things humanity has ever found to evidence that reality extends far beyond the observable universe itself. The idea sounds ridiculous. Even many physicists admit that, because the moment someone says other universes, most people immediately think of science fiction. Parallel Earths, alternate timelines, infinite copies of ourselves making different choices. The kind of concepts normally associated with movies rather than scientific journals. But the reality is more complicated. And far stranger. The multiverse did not emerge from fantasy. It emerged from mathematics, specifically from attempts to understand what happened during inflation. As researchers developed increasingly sophisticated inflation models, they encountered an unexpected consequence. Inflation might not stop everywhere at the same time. In fact, under certain conditions, inflation might never stop completely. Some regions of space could exit inflation and become universes. Other regions could continue inflating. Those regions could then produce more universes, and those regions could create even more. The process could continue indefinitely. An endless cosmic chain reaction, a self-reproducing system generating universe after universe after universe. This idea became known as eternal inflation. And if eternal inflation is correct, then our universe may not be unique. It may simply be one bubble among countless others. Imagine a pot of boiling water. Bubbles constantly form. Expand. Separate. And drift apart. Now replace water with inflating space-time. Replace bubbles with universes. The analogy is imperfect, but it captures the general concept. Our entire observable universe may be one cosmic bubble floating within a much larger structure. A structure so vast that calling it a universe may no longer make sense. And here is where things become truly unsettling. If multiple bubble universes formed near each other during inflation, collisions become possible. Not collisions between galaxies, not collisions between stars, collisions between universes. The phrase sounds absurd. Yet the mathematics allows it. Two expanding bubbles could eventually touch. The boundary between them could interact. The interaction could leave scars. permanent imprints, distortions embedded into the structure of spacetime itself, and those distortions might survive for billions of years. Long enough for us to detect them today. Suddenly, the cold spot became interesting again because one predicted signature of bubble collisions is exactly the kind of anomaly astronomers observed, a large circular feature in the cosmic microwave background. A region differing from its surroundings, a patch of sky carrying evidence of an ancient encounter. Not proof. Evidence. There is a difference. Many headlines exaggerated the idea. Some articles claimed scientists had discovered another universe. They had not. Others claimed the cold spot proved the multiverse. It did not. Science rarely deals in proof. Especially when investigating phenomena at the edge of observation, what scientists actually found was something more subtle. The cold spot possessed characteristics that some bubble collision models predicted. That does not mean a collision occurred. It means the possibility could not immediately be excluded. And that small distinction matters enormously because extraordinary claims require extraordinary evidence. The multiverse is among the most extraordinary claims imaginable. The burden of proof is enormous. Most cosmologists therefore remain cautious, very cautious. The majority view remains conservative. The cold spot is probably a statistical fluctuation. Or partially explained by the giant void. Or some combination of known effects. That remains the safest conclusion, yet the alternative refuses to disappear. Every few years new studies appear. New simulations, new analyses, new attempts to determine whether the anomaly contains hidden signatures of a bubble collision. So far none have delivered a decisive answer. The evidence remains inconclusive, but inconclusive does not mean impossible, and that distinction keeps the debate alive. One reason the idea remains fascinating is because inflation itself naturally predicts enormous regions beyond our observable horizon. Remember that the observable universe is not the entire universe. Those are different concepts. The observable universe is simply the portion whose light has had enough time to reach us. Roughly 93 billion light-years across. Everything beyond that horizon remains invisible. Not because it doesn't exist, but because light from those regions has not reached Earth yet. The actual universe could be much larger. Trillions of light-years. Quadrillions. Infinite. Nobody knows. The observable universe is merely the part we can currently see. A tiny window into a potentially much larger reality. That realization alone is extraordinary, even without invoking other universes, because it means most of reality may already lie permanently beyond our reach. Now imagine extending that concept further. If inflation produced additional bubble universes, they would likely exist far beyond our observable horizon. Completely inaccessible. Forever. No spacecraft could reach them. No telescope could directly image them. The expansion of space itself prevents contact. And yet they might still leave traces. Ancient fingerprints, scars from interactions occurring during the earliest moments of cosmic history. Which brings us back to the giant void. Some theorists have proposed a remarkable possibility. Perhaps the void and the cold spot are not independent anomalies. Perhaps they represent different aspects of the same ancient event. An event occurring during inflation, a bubble collision altering local conditions, changing density distributions, influencing future structure formation, creating both an unusually large void and an unusual microwave background feature simultaneously. Again, this remains speculative, very speculative. There is no consensus. No confirmation. No accepted proof. But the hypothesis survives because it addresses multiple puzzles at once. And in science, explanations capable of solving multiple mysteries are always taken seriously. Not accepted automatically, but taken seriously. The greatest challenge facing multiverse theories is testability. How do you test something beyond the observable universe? How do you investigate regions fundamentally inaccessible to observation? Many critics argue this is impossible. If an idea cannot be tested, they say it does not belong within science. Supporters disagree. They argue indirect evidence may still be possible, not direct observation, indirect observation, the same way black holes were inferred before they were imaged. The same way dark matter was inferred before it was detected, the same way Neptune was predicted before it was observed. Reality often reveals itself through consequences, not direct visibility. And if the multiverse leaves consequences inside our universe, those consequences may eventually become measurable. Perhaps in the cosmic microwave background, perhaps in giant voids, perhaps in some future observation nobody has imagined yet. For now, however, the giant void remains suspended between two worlds. One explanation is conventional, a rare but natural structure produced by cosmic evolution. The other is extraordinary, a surviving relic from events occurring beyond our universe itself. Both remain possible. Neither has one. And that uncertainty is what makes the giant void so fascinating. Because buried inside nearly 2 billion light years of emptiness may be one of the deepest questions humanity has ever confronted. Not how galaxies form. Not how stars evolve, not even how the universe began, but whether our universe is the whole story at all. Or merely one chapter in something vastly larger than we have ever imagined. For nearly 2 decades, astronomers have stared into one of the strangest regions ever discovered, a place defined not by what exists there, but by what doesn't, a region almost 2 billion light-years wide, a vast cosmic desert where galaxies are unexpectedly scarce. A structure so enormous that even today scientists continue debating how it formed, and after all these years, one uncomfortable truth remains: nobody knows for certain. That is not a weakness of science. It is science because the universe is under no obligation to be simple. It does not care whether its structures fit neatly into our models. It does not care whether its mysteries are convenient. It simply exists. And our job is to understand it. The giant void stands as one of those rare discoveries that forces scientists to confront uncertainty directly. Every major explanation remains incomplete. Every theory explains part of the puzzle. None explains everything. The simplest explanation is also the most conservative. The void may simply be an extraordinarily rare fluctuation, a natural consequence of inflation. A cosmic accident produced by quantum fluctuations amplified across billions of years, nothing exotic. Nothing supernatural. No hidden universes. No revolutionary physics. Just statistics, a very unlikely event occurring somewhere within an unimaginably large cosmos. Many cosmologists favor this explanation, and for good reason. History teaches caution. Again and again, mysterious observations eventually find ordinary explanations. The safest assumption is usually that nature remains consistent with known laws, until evidence proves otherwise. Yet the giant void refuses to become entirely ordinary. Its scale remains extraordinary. Its relationship with the cold spot remains unresolved. Its implications continue generating debate, and that is why more ambitious explanations survive. Some researchers believe the void may reveal subtle limitations in our understanding of cosmic evolution. Perhaps dark matter behaves differently than expected. Perhaps dark energy influences structure formation in ways we do not yet fully understand. Perhaps the largest scales of the universe contain patterns our current models only approximate. These possibilities remain scientifically respectable. Interesting. Plausible. Worthy of investigation. Then there are the more radical ideas, the ideas living at the edge of modern cosmology. Theories involving eternal inflation, bubble universes, ancient collisions between realities, concepts so extraordinary that many scientists hesitate to discuss them publicly. Not because they are impossible, but because extraordinary possibilities demand extraordinary evidence. and that evidence does not yet exist. Still, the mathematics allows them, and as long as the mathematics allows them, they remain part of the conversation, perhaps not the most likely answer, but not entirely excluded. That distinction matters because science progresses by keeping difficult possibilities alive until observation can decide between them. The giant void therefore occupies a unique position. It sits directly at the intersection of observation and imagination, of evidence and speculation, of what we know and what we do not know. Few discoveries occupy that territory for long. Most mysteries eventually collapse into certainty. This one has not. At least not yet, and perhaps that is what makes it so compelling. The void reminds us that despite centuries of scientific progress, humanity remains a young species staring into an ancient cosmos. We have mapped planets, photographed black holes, detected gravitational waves. Measure the age of the universe, yet a gigantic region of emptiness spanning billions of light years still leaves us arguing over fundamental questions. How did it form? Why is it there? What does it mean? Sometimes the most profound mysteries are not hidden inside black holes, not buried within distant galaxies, not concealed behind impossible equations. Sometimes they appear as absence. As silence. As emptiness. The giant void is exactly that, a region where the universe seems to have forgotten something, a place where the cosmic web thins, where galaxies become scarce, where matter retreats, where billions of light years pass with surprisingly little to show for it. And yet that emptiness speaks, not directly, not clearly, but persistently. Every new survey. Every new telescope. Every new simulation adds another piece to the story. And with each piece comes another realization. The void is not merely a hole in space. It is a question written across billions of light years, a question the universe has been asking for nearly 14 billion years. Perhaps the answer lies in inflation, perhaps in dark energy, perhaps in quantum fluctuations, perhaps in physics we have not yet discovered, or perhaps the answer is stranger than any theory currently imagined. We simply do not know. For now, the giant void remains exactly what it has always been. A vast region of darkness suspended within the largest structure humanity has ever observed, a place where galaxies should have been, a place where certainty disappears, a place where some of the deepest questions in cosmology continue to echo unanswered. And somewhere within that immense emptiness, stretching across distances so vast that light itself needs billions of years to cross them, the universe may still be hiding one of its greatest secrets. Waiting. Silent. Patient. As it has been for billions of years, waiting for a civilization young enough to wonder and persistent enough to keep looking.